My name is Scott Parker. I'm the lead of the Performance Engineering Group at the Argonne Leadership Computing Facility. So the Argonne Leadership Computing Facility is one of two leadership scale computing facilities operated by the Office of Science and the DOE for open science. So Judy Hill's coming from Oak Ridge, which is our sister institution. She's going to be talking about the machine they have on the floor. I'm going to be talking about one of the machines we have on the floor at Argonne. It's a Cray XC40 system called Theta, and it's based on the Intel Xeon Phi Knights Landing processor. So this is probably, looking at the agenda for today, this is probably the most traditional architecture that you're going to see. Certainly a lot more traditional than quantum computing. It's very good at multiplying numbers. People have been doing this with these machines for 30, 40, 50 years now. It's interesting because if you look at why, I put up a slide that I called from the top 500 that shows, where the Xeon Phi lives in the top 20, and you can see that there's 7 of the top 20 systems use the Xeon Phi, and the machine that I'm talking about sort of is clinging to the bottom here. Number 21 is Theta. So all these machines are using the Xeon Phi, and so while you'll notice the fastest is number 9, so these many core systems are sort of starting to drop out of the top 500. If you go back and look at the list and look at the top ones, they are predominantly GPU driven machines these days. There's still a Blue Gene Q at Livermore hanging in there. But I think what we're seeing is that many core, while it's a very important architecture in HPC and will certainly be around for a long time, is sort of at the moment lagging in the performance race to newer architectures like GPUs. But it's still very important. I mean, basically, we still have a third of the top 20 that are in the many core space. And really, if you're going to understand computer architecture, this is a great place to start because all of us, our laptops, everything, are running something similar to this kind of architecture in different forms. So I think it's a good starting place for understanding computer architecture and HPC. I don't see these systems going away anytime soon. So the machine I'm specifically going to talk about is Theta. So Theta is a Cray XC40 system. It's got almost almost 4,400 cores, or nodes, excuse me, on the system, and over 280,000 cores. Peak petaflops is just under 12 petaflops. We got this machine back in fall of 2016, so it's about 2 years old now. It runs the Intel Xeon Phi processor. This is Intel's second generation of the Xeon Phi architecture. First generation was called the Knights Corner. And we run a particular flavor called the 7230. This one has 64 cores per node, and the frequencies are comparatively low. We're at about 1 gigahertz, a little above, especially if you're doing dense mathematical operations. You're going to be using these AVX 512 instructions, so you're at 1.1 gigahertz. There's really 4 big architectural pieces that make up a supercomputer, and I'm going to talk about 3 of those 4. The 4 are the processor, the memory, the network, and the file system. I'm going to talk about the first 3 because I think those are, I know you'll be talking about I/O a lot more later in the program, and also I'm not an expert in file systems. As long as I can read my data and write my data, I'm happy. But this is where I spend a lot of my time worrying about how to use these well. And all 3 are important to the performance of the machine. And so we'll take them, we'll walk through each of these 3 areas, in the specific case of Theta. So memory-wise, we have 892 terabytes of total system memory. Now, what's interesting or different about the Xeon Phi than most other traditional, many core systems you might have been on is it has 2 types of memory. It has this MCD memory, which is fast memory, but there's not a lot of it per node, and it's got traditional DDR memory, which is slow, but there's a lot more of it. So from a programming point of view, this introduces some challenges. How do you use these 2 memory subsystems? There's advantages, but there's also complexity to navigate. And finally, the thing we're going to talk about is the network. Now, network is really what makes supercomputers super, all right? I mean, we all have, chips in our laptops. We can go and put, thousands of these same chips in a facility and say, oh, we have a combined exaflop or 100 petaflops, but you can't really use those effectively unless you have a good network. And this is a challenging area. Scaling chips hasn't been as hard. Getting flops out of them is comparatively easy than to tying them all together with a fast network. So I'm going to spend some time talking about the network on this system. I showed you a few systems back here. Not all of them have the same network, but the top two, Trinity, Cray, and Theta, all are running the Cray ARIES interconnect. The other ones are, I think, predominantly running the Intel OmniPath, but a lot of the ideas are the same. So before I get into the details of Theta, I want to take a minute and just sort of look at the history of both Argonne and many-core, and also kind of take a look at what might be coming up in that space. So if you go back, way back to 2004, I would say this is sort of the start of the multi-core era in HPC. BlueGene L system was one of the first sort of multi-core systems that really gained traction in the HPC market. For a long time, Livermore had one that was #1 in the top 500, and it had a whopping 2 cores per node, and they weren't cache coherent. So, you know, this was the early days of multi-core computing. Argonne got one of those machines, a relatively small one, but then starting in 2008, we got 40 racks of BlueGene P. BlueGene P had 4 cores per system, or per node, which was a lot in those days, and it was you know, a half a petaflop, 500 teraflops of performance. So at that time, that was enough to get it #3 in the top 500. Today, you know, that kind of power is not that much, as you'll see when you look at Theta. And then the follow-on to that was a BlueGene Q. So we have 40 racks, and we still have this machine. Pete said the life cycle of these machines is 5 years. We're trying to be the exception to that statement. We're still running Mira. Mira's going strong, and we'll probably run it for at least another year. So we're getting a lot of mileage out of Mira. This had 16 cores per node. So all these systems starting way back in 2004 have sort of just followed this multi-core architectural track and expanded the number of cores per node. And today we're at Theta, where we have 64 cores per node. We're at 12 petaflops, and like I said, this came in 2016. Now, our original plan was to bring in another many-core system this year, maybe next year, 2018, 2019 timeframe. That was going to be called Aurora. However, as you've seen, multi-cores is struggling a little bit in the top end of the HPC market, and so Intel and Argonne kind of looked at the trends and said, we need to stop and think about this a little bit. And we decided, well, you know, we're not going to do that. Intel actually has sort of revamped their roadmap and made some architectural changes to what they want to do for their HPC targeted chips. And so we're not bringing a new machine in, unfortunately, this year or next year. However, we will be bringing a machine in 2021 that's targeted at 1 exaflop. And so this will be coming from Intel, but it'll have some new features. So it won't be quite what we had planned originally. But I think it'll be very interesting. So I'm looking forward to being able to come out in 2021 and talk about that. So let's take a look at Theta and what makes Theta the various pieces. So if you went into the machine room, unfortunately, we're not at Argonne, so we can't take a tour. So I thought I'd give you a little virtual one. If you walked into the machine room, what you'd see is 24 cabinets that house all the nodes. Like I said, we have about 12 petaflops of peak performance. Each cabinet holds 192 nodes and has 510 teraflops of performance. Now, if you remember, I mentioned our BlueGene P system that came back in 2008 was 40 racks, and it had about 500 teraflops. So we get all the power that was in 40 racks basically 10 years ago, now in a single cabinet of KNL. So you can see how much this, these architectures have progressed over just 10 years. If you open up a cabinet, you'd find 3 chassis, and each chassis has 64 nodes and 16 blades, and a blade holds 4 KNLs. Now, I mean, from a computer architecture point of view and from a software development point of view, this kind of stuff is often not that interesting, how they package these things, but having seen the work that goes into this is actually quite a complex problem. Power and cooling to these systems and keeping the floor space at a reasonable level, so that these machines aren't taking up a football field. It's actually quite hard, and the amount of power that these racks are consuming now is getting up into the kilowatts. The amount of heat coming off them that you have to dissipate, really makes cooling these things very complex. So if anybody's a mechanical engineer like I am, the process of pulling all this heat off of these systems, these very dense layouts, is increasingly challenging. But really, from an architectural point, what we care about is sort of when you go down to pull apart the blade, what you find in there is you find this ARIES chip. This is our network router, so this is how all your data flows across the machine. And then to that network router, 4 of these KNL chips are connected. So I'm going to dive into the chip in more detail, but I kind of wanted to take a moment just to give you sort of the big picture features that make the Knights Landing distinct from some of the other Intel processors, and certainly from its predecessor, the Knights Corner. So first of all, it's self-booting. So I don't know if anybody ran on the Knights Corner, but it was really just an attached coprocessor or an accelerator. So you had to have a Xeon or something else there. And so it really had, then you had this whole issue of offloading and kind of things like that you had to program to. The KNL's not like that. So it's just like a regular Xeon system. It's got 64 cores. Your OS runs on those cores. Everything's there. So it's comparatively simple in that respect. It's binary compatible with the Xeon, so you don't have to do anything fancy to get a legacy code. You can port your binary over there, and it'll run right out of the box without recompiling. Now, there's advantages to recompiling because it has things like the new AVX512 instruction set. So this is the first Intel processor that supported their new AVX512 instructions. So this can do 8 floating point operations per cycle on a single SIMD instruction. This is starting to proliferate through the Intel line, so the newer Skylakes have these instructions, but the KNL was the first one to provide it. Overall, the chip peaks out at about 3 teraflops per chip. If you look at GPUs, they go a bit higher. They're in the 5 to 10 teraflops per socket range, but also their power consumption is higher. One of the reasons the power on these machines isn't so bad is that they're using sort of a lightweight core. And if you go back to the Blue Gene line that I talked about that Argonne had, this was a feature of those. Intel has this, what was their mobile line of processors, and I think they've sort of given up in mobile space and ceded it to the ARM processors. But this was Intel's play for trying to put their chips in your cell phone. And to do that, it had to be very power efficient because you want your battery to last all day or multiple days. And so they adopted these cores to the KNL. Along with that, they added some unique architecture features like gather scatter engine, and then this new memory architecture with the fast and slow memory. And they also built in their interconnect. So Intel has an OmniPath interconnect. They built the NIC right into the chip. It's PCIe attached, so it's not sort of tightly integrated, but it's on the same chip. This point on the same chip. And finally, and I'll talk about this more, is the on-die interconnect. So tying 64 cores together and getting them to all work together is sort of one of the bigger technical challenges of making a multi-core chip. It's easy to sort of stamp out multiple cores, but getting them to talk to each other well and have good performance is kind of one of the trickier aspects. So I mentioned the Atom core, right? So why did Intel go with a sort of like comparatively wimpy core for their high-end HPC processor? The answer is 2 things. First of all is power. That's sort of driving, HPC design these days. It's all about power. I mean, anybody can put a big system on the floor with Xeons and get a lot of performance, but they'll be paying, through the nose for power. Just for reference, most HPC architectures these days are sort of big, top 10 systems are in the 2 to 10 megawatts of power consumption. And at Argonne, we pay about $1 million per megawatt year. So if we put our Blue Gene Q system, I think, is a little over 2 megawatts. So we pay about $2 million in electricity for that machines. The future exascale machines are looking at 20 plus megawatts per year. So you operate that machine over 5 years, you're talking about $100 million for electricity alone just to operate it. So power is sort of the driving constraint of the architecture in these machines. So all these things that you see people doing, you're saying, why are they making it so complicated? Why are they doing this GPU thing? Why are they doing FPGAs? Why are they doing this? It's because of power. I mean, if we wanted to go to exaflop in a Xeon architecture or beyond, we'd have to put a small nuclear power plant next to our computer to keep it running. And obviously that gets very complicated and very expensive. So, so if you're going to use lightweight cores and try to get power efficiency out of them, one of the main ways to get performance is through parallelism. So if you look at how do I get parallelism on these systems, you'll see it across many, many levels on the system from the node level. So we use MPI, right? We have 4,400 nodes on Theta. So we use MPI to make them all talk to each other and work together. On other types of systems, you may have multiple nodes, multiple sockets on a node. So you may have 2 Xeon processors attached to the same memory on the same node. On KNL, they don't make anything like that. So KNLs are all single socket systems. So that's really not applicable here. But then they have parallelism across the cores within a socket, and that's what KNL is doing a lot of, right? We have 64 node cores on Theta. You can get up to 72 on a KNL if you get the high-end one. So this is really where a lot of the parallelism on KNL is manifesting is on the cores and on the socket. But it's not just there. Once you go below into the core, you'll see that there's multiple pipelines that do multiple operations simultaneously. The KNL has 6 pipelines, and so it's trying to do sort of 6 things at once in different pipelines. And in those pipelines, it's feeding instructions that, some of which can be these vector instructions, these SIMD instructions. And each of these SIMD instructions can do 8 operations. It has 8 vector lanes. So they're trying to do 8 operations in a single instruction and to do multiple instructions at the same time in different pipelines. And then finally, within an instruction itself, you can do more than one operation. If you've heard of the floating point multiply add instructions, that does a floating point multiply and an add in one instruction. So if you do a vector floating point multiply add with the AVX512, you can have 8 lanes plus 2 floating point operations. So you can do 16 floating point operations in one instruction on the machine. So this is really where your performance comes from. And this is what we saw in the Blue Gene all along. The cores by themselves, the nodes by themselves may not be that powerful, but once you start getting hundreds of thousands of them with all these levels of parallelism, you really start to get performance. And so as a programmer, this is what you want to do, is kind of dig into your code and express as much of this parallelism as you can across all of these levels. I mean, it's great if you can get parallelism up here. If you can't get MPI parallelism, then you constrain the performance you'll get from one node. But that's just the start, right? You want to get parallelism across each core within the socket. And then this is kind of delving down into the microarchitecture. So this is usually less obvious to developers. But there's a lot of parallelism down here too, right? That you really want to get. I mean, I said like 16 floating point operations per instruction across multiple pipelines. You know, there's 32-way parallelism in there that you can express. So if you're getting the worst case of just, you know, sort of one instruction per pipeline, you know, per vector length and not using FMAs, you know, every clock tick you'll get one instruction or one floating point operation performed. If you can get, you know, all the pipelines working using all the vector lanes and FMAs, you can get up to 32 floating point operations performed per cycle. So that's a big jump from 1 to 32. Okay, so I want to start looking at the chip. Later we'll talk about the memory and the network, but I want to start with the chip. And I'm going to kind of start from the outside and work my way in. So we're going to start with the big picture and then delve down into the tile level itself. So the chip is relatively large. It's got 8 billion transistors. It's on Intel's 14 nanometer process. As I mentioned, it can have up to 72 cores. So these blue boxes are all tiles. And these tiles contain 2 cores each. So there's 36 tiles. And collectively, they can generate, you know, up to, or perform at up to 3 teraflops per node. The tiles are connected by this 2D mesh interconnect. So this is a grid of, you know, traffic or lane, you know, wires that allow traffic and data to flow. So this is like a, you know, kind of like a city grid, like if you can think of it like New York or downtown Chicago. And one of the problems here is how do you manage the traffic, right? So it's easy to stamp out cores. Doing that without creating gridlock across the die by everybody trying to drive on the same road or getting congestion at the intersections is I think, a trickier technical challenge on some levels. Around the periphery, you'll see the other pieces. So the tiles are all kind of in the middle on the left side and the right side. This is your traditional DDR. We have 6 channels. So these DDR chips live off the core. You know, if you found the board and looked at it, you'd see physical DDR chips sitting on there. So they're connected to 2 controllers, and each of the controllers has sort of 3 pathways to the chips, or, you know, 6 lanes total that lets you talk to the DDR. And from that, you can get about 90 gigabytes per second of bandwidth, which is not great bandwidth, but it allows you to have up to 384 gigabytes of total memory, which is a fair amount of memory. At the top and bottom, you'll see these things marked MCD RAM. These are the on-chip memory that Pete talked about. So this is memory is sort of physically bonded to the die, and it's in the actual, you know, chip itself. And there's 8 stacks. The downside to them is you only get 16 gigabytes of memory, but it's very fast. It's almost 500 gigabytes per second, so almost 5x what you get in terms of memory bandwidth performance from the DDR. So if you're programming on the KNL, you definitely want to take advantage of the on-package memory. And finally, as I mentioned before, Intel has their own networking that we don't use on Theta. We don't have OmniPath network installed there. We have the Cray ARIES interconnect. But if you're on other KNL systems, you may be using their on-die OmniPath interconnect. So I mentioned the KNL comes in a few different flavors. If you run at other facilities like NERSC or Trinity out of Sandia, they would be running the 7250, so that actually has 68 cores. So anytime I say 64 cores, if you're running somewhere else that has this flavor, you actually have 68. Slightly higher frequency. Our 7230 sort of sits in the middle here with 64 cores. And the high-end one that I've never actually seen or run on is the 72-core variant that runs at a slightly higher frequency. Okay, so I mentioned this interconnect, this mesh interconnect. And this is really what lets the chip work together, and all the tiles and all the cores and all the memories talk to each other. So it's a 2D grid, and the idea is that when you ask for data or send data, your data will move along the vertical axis first, along one of these vertical lines, and then if it needs to go somewhere over to like this memory controller and it's starting at this tile, go vertically, make a turn, then go horizontally to get to that destination. And this is pulling together the tiles, the MCD RAM controllers, the DDR controllers, and then the I/O that's going off chip either through the network or other devices. All this is cache coherence. So cache coherence means that if one core updates a data value and some other core, and it's sitting in that core's cache, so let's say this guy updates the value variable A, and this guy over here, one clock cycle later, wants to read the value of A. Well, the value of A is sitting over here. The whole network and the cache coherence will make sure that this guy, when he reads A, will get the same value that this guy wrote. All right, so you have to make sure that all these local caches, that may hold replicas of the same data in various places are maintained in a consistent state, so that if you do a read following someone else's write, you get the correct answer that someone wrote. So that's one of the features and complexities in these many core architectures, is how do you manage this cache coherence as the core count scales. So I want to talk a minute. If you run on one of these machines, you may have seen that this traffic issue, to mitigate it, Intel implemented a couple different configurations on the chip. So if you run at different facilities, you might hear things like, well, you can boot this chip in all mode, quadrant mode, or Sub-NUMA clustering mode. And I just want to take a moment to talk about what those are. And these are really different configurations to manage the cache coherency and the traffic on the mesh. So the first one is all-to-all, and this is basically has no affinity between the processor, the cache directory, and the memory where the physical memory where the data may be living. So the idea is that if I access a piece of data on this tile and I miss in my local cache, I need to find it somewhere. It could be in memory, it could be in someone else's local cache on another tile. So I have this distributed directory that tells me where everything lives. So there's this distributed directory that's associated with, a little piece of it's associated with each tile. And that knows where, it keeps track of where every bit of data is living. And so if I miss a reference in my local cache, I'll send a request to the distributed directory saying, hey, where is this? And this distributed directory can be anywhere on the chip. And so you may have to transfer all the way down here. You find that, oh, okay, well, it says it's not in any of the local tile memories. It's up in the main memory and that MCD RAM controller up there. So then that request gets forwarded up to that corner where the data is loaded, pulled out of memory, and then sent back to the tile that requested it. So you can imagine if all 64 cores are doing this, you can generate a lot of traffic on this mesh. And so this can cause, performance issues. And so to mitigate this, they implemented another mode called quadrant mode. And this is really probably the most common one you'll see. And this tries to create an affinity between where the cache directory is and where the memory that's holding that data would live. So the idea is you're no longer kind of transitioning or sending data quite across as much of the chip anymore. If you have a miss, you'll still have to go to a distributed directory, but that directory may be up here, closer to the memory that's actually holding the data value. And so you have less traffic on the chip. And this is probably the most common mode you see it running. The final mode is called Sub-NUMA clustering, where it tries to creates an affinity between all three things: the tile, the directory, and the memory itself. So if you use this well, you can constrain all of your on-chip traffic to one quadrant so that you're not sort of creating as many traffic jams. Now in practice, what we see is there are some advantages to using this, but usually not enough to offset the sort of difficulty in trying to program this well. So most machines are booted in quad mode and live in quad mode. All right, so let's move down to the tile. So if we kind of pry open one of those tile boxes and look at what's in there, what we would see is we see two cores that share a 1 megabyte L2. And attached to each core is a vector unit that has two vector pipelines. And there's also this CHA, this cache homing agent, that keeps the distributed tag directory, manages the coherence from the L2. and puts the data on, takes the data on and off of the interconnect mesh. So let's take a look at one of the cores in a little more detail. So as I mentioned before, the core is based on the Intel Atom core, and the particular flavor is called the Silvermont. This architecture is capable of issuing or decoding and fetching 2 instructions per cycle. So, whenever you compile your code, it gets turned into a bunch of assembly instructions. So you may have, look at the total number of instructions you have to issue in the, to execute your program, maybe some number of trillion or billion, let's say 1 trillion instructions, right? This can issue 2 instructions per cycle if everything's going perfectly. So, how many instructions per cycle you can issue really is a direct determinant of how long your code is going to take to run. Other architectures can do maybe, like if you run on a Xeon, it may be capable of doing 6 instructions per cycle. So this is one of the sort of places where the Atom sort of gives something up to the Xeons, is it's more limited instruction decode and issue with. However, once you've sort of pulled the data out of the instruction cache, so when you compile your code, it goes into assembly, that goes into memory. And as you start to execute it, that data gets pulled into the instruction cache so that it's available to quickly access for the processor to use. So it's pulling instructions out of the instruction cache up here and fetching it and decoding it, deciding what that instruction means and where it should be routed. And the places it can route it to are there's 2 integer pipelines, 2 load store pipelines, and 2 floating point pipelines. So this is where the work occurs, right? So if you're doing a floating point multiply add, it's going to go over into one of these 2 floating point pipelines. If you're doing a memory load or store, that instruction is going to get routed into the memory pipelines, and the memory pipelines are attached to the data cache, the L1 data cache, which is 32 kilobytes. And if you're doing integer operations, like let's say you have a loop counter, n is 1 to 1,000, and you're incrementing that loop counter, that's an integer increment or an integer add. So that would be routed to the integer pipeline. So you have 2 of each. And the idea is that for good floating point performance, or if your code is not floating point focused, let's say it's integer memory bandwidth bound, you really want to be sending as many instructions per cycle to all these pipelines as you can, with the constraint that you can only ever issue 2 instructions per cycle, period. One of the features of this architecture that you've probably seen on other architectures is this idea of hyperthreads. So we have these 6 pipelines. We can run one thread or process on a core, and it can try to utilize all these pipelines, but a lot of times it's going to stall on memory references. So you try to load some data from memory. That memory is effectively far away, and it may take hundreds of cycles for that data to arrive back to your tile, because the request has to go across the mesh into the memory and back. And as a result, you're sitting there, your thread's going to sit there idle, not issuing any instructions, because it can't do anything until it has the data that it needs to do the work. One of the ways you can keep the core busy is to have more than one thread active, thread or process active on the core. So you can load up to 4 hyperthreads onto a core. So let's you have like 4 threads that are doing different things using the same hardware. So they're all trying to sort of simultaneously share these 6 pipelines. And if one is stalled, the other ones can keep going. And if, let's say, 3 of them get stalled, one of them's still working, keeping the pipeline going. And that lets you keep the core busier and get more throughput overall. The downside is they're sharing things like the data cache and the instruction cache. So as you add more threads, they start to divide up the resources on the core, and you can actually get lower performance in some cases as a result. So I mentioned the instructions that the KNL implements. So Intel sort of has a fairly rich instruction set, and they've been adding it to it over the years. So if you go back a few years, especially things focused on floating point and vector floating point instructions, they had the MMX, the SSE, and the AVX. And these are all sort of instructions that are trying to express more parallelism in an instruction to do more floating point operations in one instruction issue. And the idea is they keep kind of adding wider vector operations and more richness to the instruction set to express more things. So as we go up to the older Haswell, Broadwell, they had this AVX2, and then we get to the Xeon Phi, it adds the AVX512, and Intel sort of divided this into different flavors of AVX512 that in some cases are unique to the KNL. So if you compile your code and you're using this AVX512 PF, which is the gather, scatter, prefetch instructions, These aren't currently implemented on any other architecture, so that code, if you tried to move that binary, wouldn't necessarily run on those machines. And some of these other newer architectures are adding new extensions to AVX512 that aren't on the KNL. Most of these are sort of more exotic corner cases that you probably won't use in practice. So the main thing to take away from here is that, you know, the KNL is sort of supporting the main flavors of vector instructions that Intel provides, and, you know, has the AVX512 in it. Okay, all right, so this is going to kind of conclude my discussion of the processor side of the chip, and I just wanted to give you a sense of what the performance you might expect to see, at least at the upper bounds from the chip is. So one of the sort of most floating point intensive benchmarks that you can run is the matrix multiply. So matrix multiply has a lot of floating point operations per memory reference. On Theta, the peak floating point rate is 2.2 teraflops. That's using all 64 cores, using 2 vector pipelines, 8 wide vectors with the FMA instructions at the frequency of 1.1 gigahertz. If we run an MKL DGEMM, so this is Intel's optimized math library, and DGEMM is their matrix multiply implementation, we can measure a peak of just under 2 teraflops of performance, or about 86% of peak. So this is basically about as fast as you're going to be able to push the chip. If you look at how the performance varies with the number of threads, we didn't quite include all the possible ranges, you know, 1 to 64, but, you know, this line, for instance, is using 32 cores. If you use 32 cores, you get about half the performance that you get using all 64 cores, which is the blue line. So 64 cores is the most number of cores you can utilize with 1 thread per core. As I mentioned, this chip has hyperthreads, right? So we could load up and put more threads on a core. So we could go to 128 by putting 2 threads per core, 256 by putting 4 threads per core. And as you see, though, in this instance, it doesn't really help much at all. The performance is basically the same. And that's because, you know, those 4 threads are still using the same resources that are on a single core. So those 2 vector pipelines, all they have to work with. So even though you have more threads, they're sharing now the 2 pipelines. So they only each get to use it a quarter of the time. So in this case, since DGEMM is not really you know, limited by memory bandwidth or memory latency, it's really just memory limited by instruction issue, having more hyperthreads doesn't help you. Now, there's other instances of kernels that I could put up here where having the hyperthreads would help. But really what I'm trying to show you is just, you know, what kind of performance you could expect to achieve at the sort of higher limits on this platform. All right, so I want to shift now to looking at the memory. So I think the memory is sort of one of the features that's newer and a little more interesting on the KNL, because really one of the challenges in HPC has been memory bandwidth. This off-chip memory, you know, as I mentioned, we have 90 gigabytes per second coming from the DDR. It's sort of a very thin straw for these really fast cores, these 3 teraflop nodes to be you know, drinking data from. And this often becomes a bottleneck. So if you run an HPC code, you know, you may be very focused on your floating point performance, but often it's not the floating point performance that's, you know, the floating point performance of the chip that's limiting you. It's the rate at which you can pull data out of the memory that's limiting your performance. So a lot of codes are memory bandwidth bound. And so they, you know, chip designers are taking steps to try to mitigate this. And I think, you know, looking in the future, 5, 10 years from now, I'm guessing in HPC, you won't see a lot of off-socket DDR, this traditional DDR4, DDR5, that are discrete separate memory chips will probably go away. And you'll have only on-package memory. The issue right now is that it's expensive and their ability to create it in large volumes is limited, so you can't have a lot of memory today on a chip. So the KNL is sort of taking a baby step in that direction, where what they've done is they've put 2 types of memory. You have a core, which is connected to L2. If you miss in your L2, you can go and look in and hopefully find your data in one of these 8 MCD RAM stacks that are, you know, physically on the chip and have comparatively high bandwidth. If not, if your data is living on the DDR, you're going to have to go to one of the 2 DDR controllers and pull it off there. And as I mentioned, there's this 5x performance difference in terms of the bandwidth that you can achieve between the DDR at 90 gigabytes per second and the MCD RAM at 85 gigabytes per second. So the question is, okay, you have these 2 memory spaces. How do you as a programmer utilize them? And you have some options, just like we had with the tile configuration for all-to-all quad and Sub-NUMA clustering. You have configuration options when you want to use this memory. So you can use them as 2 distinct memory spaces where you explicitly decide where you want to put the data, or you can do use the IPM essentially, or this in-package memory. Where it says IPM, this is the same as, that means in-package memory, which is the MCD RAM. That's the specific type of in-package memory that's being used. You can use the IPM as a cache. So there's basically 3 modes that you can put the chip into when you boot it up. The first mode is cached, and so that's the first picture here. You have the CPU, it has 480 gigabytes per second to this IPM, and then IPM is basically caching the data that's in the DDR. So if you reference something in the DDR, it'll get pulled out, stashed in the IPM until that gets full, and then it'll start knocking things out. So it basically acts as a big last level cache. So if you run the chip in cache mode, that's what it's going to be doing. Alternatively, you can say, I don't want to use this cache mode. I know how to lay out my data better than it would be in cache, so I'll run it in flat mode. In flat mode, there's no caching in the IPM. You essentially have 2 NUMA spaces on the chip where you can explicitly malloc your data into the DDR or the IPM. So you as the programmer would choose, I want this piece of data to live in the IPM. I want this piece of data to live in the DDR. With the idea being that the things that you need to have access to using high bandwidth, you put in the IPM, and the other stuff you put in the DDR, because it's maybe stuff you don't reference that much. Maybe it's where you put your checkpoints or big tables of data that you rarely address. And the final mode is a hybrid mode where you sort of partition the 2 and you say, well, I still would like some of this cache for my IPM, so I'll put maybe a half or a quarter of my IPM as cache in front of my DDR, but then I'll explicitly manage the other remaining parts. And there's the libraries on the system, JEmalloc and memkind, along with the NUMA control command that let you sort of, again, place the data in the part of the chip that you want to have it in. So a very common way of sort of talking about memory performance is with the stream benchmark. So the stream benchmark is widely used, and it basically just does bandwidth-intensive kernels and measures how fast they go. On most machines, it's pretty easy. You get one number. On this machine, it's a little more complicated because we have both these 2 types of physical memory, and then Intel has multiple types of instructions that can access the memory. So we kind of end up with this table that talks about, well, are you using MCD RAM or DDR in flat or cache mode? And then are you using Intel's regular memory access instructions, or there's special ones that are called streaming stores? And you can see that the numbers you get are different depending on what you're using, and they can differ considerably. So the ones that are in bold there are the best ones we can get using flat mode with the Intel streaming stores. Now the streaming stores I'll talk about in a second, but if you use those, you can get basically the peak bandwidth that I mentioned before, nearly 590 from the MCD RAM and DDR. We haven't really seen much difference in this from the quad SNC 4 modes that I talked about. If you're running just from a single core, right? So we have 64 cores. If you're running from just one core and run stream only on one core, you're only going to get about 14 gigabytes per second of bandwidth. So one core can only drive 14 gigabytes per second. So you have to use sort of all the cores collectively to really get the full bandwidth out of the chip. Now I mentioned both that we can boot the system in flat mode or cache mode. If we boot it into cache mode and we use the IPM to cache our data, our memory bandwidth drops. All right, and this is a result of the fact that it's this flat mode configuration is nice, it's convenient, but it has additional overhead, and so it lowers your memory bandwidth that you can achieve. Finally, there's this idea of these specialized instructions for streaming stores. And what these instructions do is they tell when you store something, it says, don't put this in the L1 or L2 cache, just send it straight to memory. And this sort of lowers the overhead of doing these memory operations. It takes out a read for ownership operation that needs to happen. I won't get into the details of why that is. But just you can think of it as a more efficient way. If you're not going to reuse the data soon, it's a better way to send the data, a more efficient way to send the data to memory that lowers the overhead and can improve performance. So if we don't use the streaming stores, we drop down to, in flat mode, about 2/3 of the bandwidth that we could otherwise have. In cache mode, it doesn't make as much of a difference. So if you're doing memory bandwidth intensive codes on KNL, there's 2 things you want to think about is, do you want to be in flat or cache mode? And then do I need to keep this memory data around, or can I use these more efficient streaming stores to push it out to memory more quickly? The other part of memory that we want to look at is memory latency. That's basically how long does it take from when you issue a memory request to get the data back. And the answer is depends a lot on the locality. So how close is the data to you? If it's in the L1 cache, it's 3 nanoseconds, so about 3 cycles. If it's in the L2 cache, it's about 15 cycles. If it's in the MCD RAM or the DDR, you're talking 100+ cycles to get this data. So cache locality is critical for performance. If you have to wait 100 cycles, for your data to come back. That's 100 cycles you may be doing nothing, right? So you're going to get 1% a peak at best on the machine. And this all has impact on other things that you may not think about immediately. For instance, the OPENMP overheads. The KNL has no last level cache, so the OPENMP overheads sort of are proportional to the time that it takes for memory operations, and so this is where it has to go to fully out to memory. So if you're doing OPENMP barriers, let's say, reductions, you can see that they, with one thread, they're about under a microsecond. When you get up to 256 threads, they get up to the tens of microseconds. And actually, we found that the scaling on this system is, to the number of threads to the square root of the number of threads. So if you're doing OPENMP, this is what you can expect to see for OPENMP scaling on this machine. I don't have a lot of time, but I want to go quickly through the network, because like I said, this is really one of the unique features of this particular architecture, not just of the KNL, but of the Cray XC40 line. And it's also a critical piece to getting performance out of your system. So the Cray uses, the XC40 uses the Cray ARIES interconnect. So 4 of these KNL nodes are connected to a single ARIES router, which has 4 the NICs on it, plus 48 tiles or ports that go out to other parts of the network. And the configuration is called a DRAGONFLY. Now, DRAGONFLY, it can be a little confusing at first, but the idea is DRAGONFLY breaks the machine up into groups. So our machine has 12 groups. Within each group, you have very rich connectivity, and the nodes are laid out in sort of this virtual 2D grid with 16 in one direction and 6 in the other, for a total of 192, I think, nodes inside a group. And there's basically all-to-all connectivity. So if this node wants to talk to this node, it has its own dedicated link that goes there, and it can achieve full bandwidth between those 2 nodes. If it wants to talk to somebody who's sort of not in the same line or column, it has to make a hop. So it has to go across and then up. But you can see there's a lot of lines here, right? There's a lot of connectivity. There's a lot of bandwidth within the group. At the group level, we also have all-to-all connectivity. So this group may have 2 links of the same speed as these ones going between this group and this group. So it has links going to all groups. And, but it may only have 2 links going between 2 to 4. I can't remember on Theta. I think we have 4 links going between groups. So within here, this node has 16 links coming off of it, connecting it to all these guys, and another 6 going up here. So it has a total of 22 links coming out to talk to other nodes. But this whole group only has maybe 4 links to talk to all of the nodes in another group. So the idea is you want to have some degree of locality in your computation to really take advantage of this rich bandwidth within the group. And then you got to be careful when your nodes are scattered across groups, because you're going to have a thin pipe between each group. So I know there's going to be another talk. Ken's going to be talking about MPI a lot, so I won't go into details here. But I did want to talk about the performance you can expect to see on these systems. So this is MPI send and receive performance on Theta. So this is the number of bytes on the horizontal axis, and this is latency. So you can see that one of the things I mentioned is how far away 2 nodes are depends on, are they in the same group or if they're different groups, and if they're in the same group, are they in the same row or same column? So the number of hops through the network that a packet might have to take can vary from essentially 0 to 5. So that would be the distance that they are. And so we went ahead and we measured the latency for MPI ranks that were positioned different distances apart. And what we found is that it doesn't vary that much. There's a little bit of a difference between nodes that are in 2 different groups that have to take the maximum number of hops and ones that are on the same group. But it's pretty minimal. And so our latency sort of starts at about 3 microseconds. So that's about 3,000 clock cycles to sort of send a piece of data from our node to another node. So if you think about the L1 cache latency, it was about 3 cycles. To get to memory was about 150 cycles. If we want to go to another node, it's about 3,000 cycles just to send our data there, not to get a response back. So this is why communication can be a bit expensive. Looking at this, I always find these tables and just these plots a little hard to sort of keep in my mind. And one thing you'll notice about this, it has this odd kink, right? Like, it's actually really 2 different lines that are sort of stitched together. Because what the hardware is doing, and I think Ken will talk about this a lot more, is switching between 2 different protocols for communication between ranks. There's one called eager and there's one called rendezvous. Rendezvous's got a little bit more overhead, but it can be sort of better for large message sizes. And eager's a little faster, but it sort of has limitations that limit it to small message sizes. So these 2 graphs are sort of stitched together, and the hardware makes a crossover. And if you look at the Cray documentation, it's at 8192, which is exactly where we see this kink. If we look at the hardware itself, though, if we do an MPI one-sided operation, which is this gray line, we see that it's able to maintain a lower latency using these one-sided operations that don't have this hardware this protocol switch. And this fits a nice model. This is sort of, you can look this up in literature. It's often called the Hockney model, where the time to send a message is alpha plus beta n, where n is the number of bytes, alpha is some minimal latency that you're stuck with even at 0 bytes, and beta is the cost per byte. And we can kind of take that graph and look at it another way, which is, all right, if I want to send a lot of messages, how quickly can I send messages? And there's another benchmark called million messages per second. So if you're sending a lot of small messages, the rate at which you can do it is often constrained by how many nodes, cores you have sending those messages. So if you're just using one core, you're sort of down here about 1 million messages per second. And if you're using all 64 cores, you can peak it out at close to 25 million messages per second. And your aggregate sustained bandwidth that you can get off the node is about 12 gigabytes per second. There's some dependency on the number of cores you're using, but you can get it up to 8 with just using one core. So real quickly, I just want to talk about the collectives performance that you can expect to see on Theta. What we found is that people tend to use just a handful of the collectives that MPI implements. This is sort of relative call frequency from some data sets that we looked at that span a bunch of applications. All reduce is by far the most used collective operation, followed by broadcast, followed by barrier, all to all. Once you get sort of past these top 5, people don't use the remaining collectives implemented by MPI very frequently. I mean, all codes are different, but if we look at the sort of overall call set, application set, we tend to see that these are the most commonly used ones. So I think I'm out of time, so I'm going to kind of go through this real quick. But these slides are available online. You guys can look at it. And this sort of shows you what you can expect for MPI barrier performance on Theta. So this is the number of nodes. This is the latency. You can see it starts at about 20 microseconds, so a lot longer than just sending a single message. And it fits this model where it's sort of very similar to the message cost model, except there's this log 2p factor, which is p is the number of nodes. So you'll see this commonly across all the collectives. The cost of a collective scales to the log 2 of the number of ranks or nodes that you're using. This is broadcast, so it has a similar thing. And one interesting thing is you can see in all these things there's this kink. This is a model that has, that fits that curve, and this is the actual data. And it's got this kink right around where that rendezvous to eager transition hits. But otherwise, these simple models actually capture the behavior pretty well. It's essentially the cost, so broadcast is the cost to send a single message times log 2p, the number of nodes that you're using. So, and then all reduce is very similar. With that, I'll just conclude on this issue of power that I touched on earlier. So when this machine came online, it was number 7 on the Green 500, so this ranks the most power efficient systems. And what we saw is you get the most sort of performance per watt when you're using just one thread. If you use all 4, the overheads of juggling multiple threads sort of eat into your performance and your power, and it drops you down. And then using MCD RAM to move data, or to store data, moving data from MCD RAM is a lot more power efficient than moving data from the DDR in terms of the cost per byte moved. And with that, I'll conclude, and I think maybe I have time for one question.
Yeah, so you mentioned the memory modes and the cluster modes, and can we only control this during the boot? And if yes, then how do we know which mode the machine is working on? And do we need a especially like optimized code to work on different modes?
You can optimize your codes for the different modes. The machine should be, on ALCF machines, the queue name that you submit to will tell you kind of what so it'll say like cache quad in the queue, and so the queue name will tell you what mode your job is going to be running in, and you can request a different mode, but you're going to have to pay a boot time. And generally speaking, the cache quad mode is sort of the default that we kind of run things in because it works the best for everybody. If you want to do something other than that, you probably have a little work to do to figure out how to optimize your code for that. There can be payoffs, but it'll take a little bit of work to make that happen. And the best thing to do is, if you want to understand that, try it in different modes, see which, if any performance difference there is, and then sort of start looking into the performance to see if there's ways to optimize it for that.
On the memory latency chart you put the MCD RAM said it had a higher latency than DDR RAM.
Yeah, it actually does have slightly higher latency than the DDR. Not what you'd expect, but that is true. Though I should say that there's a caveat to that once you start to really bang on it really hard and load it up, those will switch. So the MCD RAM sort of will stay, its latency will stay constant no matter how how much you're bombarding it with memory requests, or relatively constant, whereas the DDR, I think, spikes up quite a bit. But if you're just doing sort of like a single memory reference to memory, yeah, it is, the latency is, so the aggregate bandwidth can be higher, but the latency of an individual reference can be longer, and it's just the parallelism that makes a difference.